Final exam review for Unit 2. Let's begin with the very first lesson we did in Unit 2. Let's arithmetic and geometric sequences. Do you remember the formula for solving these that I gave you for? Let's start with arithmetic. What does it mean to be arithmetic?
Adding or subtracting.
It's adding or subtracting. So sequences that add or subtract. And what's it mean to be geometric? Okay, and that's going to give you a hint on the formulas. They all start the same. How did they start? It's A, N, which means to find any term, you start with the initial term or the earliest term, which what do we use for that symbol? AK. Because these are adding, you can plus D times N minus K. That was it. There's the formula. The only difference with geometric, we do use G instead of A. At least I should say College Board did, is they use a letter G. So they would say Gn equals Gk. So they start the same, but here's where they go different. These aren't adding and subtracting. What did geometrics do instead? They multiply by R to the power of N minus K. There's your formula. Anything you need from that, you can manipulate that formula. So for example, if I gave you two terms and I wanted to know the common difference, just manipulate the formula. If you wanted the common difference, how would you get rid of the AK over here? Say it again. If you wanted the common difference, how could you get rid of this AK? Subtract. So if you subtracted AK from both sides, what you could also say is that AN minus AK will equal the common difference of N minus K terms. And divide by N minus K. And so we end up with D equaling AN minus AK over N minus K. It's almost like your slope formula. Change of y's over change of x's. It's the same premise there. So the blue is the actual formula for arithmetic sequences. On the right, we solved how you would get your D isolated. Okay, what about in GK? What if you had to solve for the, geometric? What if you had to solve for the rate there? What would you do to isolate to get the rate? Before that, gotta do something first. Divide. So if that's multiplying, you would divide by GK. Divide by GK. And so we could say R to the power of N minus K would equal Gn divided by Gk. If you were actually looking for R, you wouldn't have to log. If you think about it, if you had an N and a K, let's just say I had two numbers here, a 10 and a 2. You say 10 minus 2 is 8, and you can do it 8 groups. So you actually don't have to convert to a log here. Questions there? Can I move on? So we got a lot of material to cover. We did 15 lessons. That was the first lesson. I'm going to skip lesson 2. Lesson 2 tells us that arithmetic is very similar to what type of function? Arithmetic is like linear, and geometric is like exponential. I'm skipping that. I'm not going to review that. So I'm going to go into now lesson 2-3, starting with exponentials. I'm actually going to blend in a lot of the exponentials and its equivalent logarithm lesson. Looking at the graphs, is this an exponential graph or a logarithmic graph? It's exponential. And I'm going to remind you why. There's 3 things that are very important for every exponential. This is an exponential function. How do I know it's exponential? The easiest way to tell is it's right here. The easiest way to tell if it's exponential or logarithmic is to check out the asymptote. If it's exponential, it's horizontal. If it's logarithmic, the asymptote is vertical. What's my asymptote this time? Do I have a horizontal asymptote or do I have a vertical asymptote that the graph's approaching?
Horizontal.
Horizontal. Add that. Oh, you don't have a packet. Sorry, what am I saying? If you're doing a quick sketch, if you do a quick sketch, just so you know what you're looking for, very quick sketch, make sure, more important than the points, is to put that it has a horizontal asymptote there. So if you just want to draw the curve up, with the horizontal axis. Horizontal asymptote, I should say. It's an exponential function. We know it's an exponential function because it has a horizontal asymptote. That's the key that gives it away more than anything else. What's the equation of this asymptote? Would it be an x equals or y equals, do you think?
X equals.
A lot of people think x equals because it models the x-axis, but it's not. Because the x's are always changing. For example, right here, the x is -5. Over here, though, the x is +5. The x is changing, but you know what's not ever changing? The y's. What are y's at both points? What's the y value both here and there? 0. It's the x is -5, then the x was +5, but the y never changes. The y was always 0. Other key points that you should know is an exponential function without a transformation goes to the point 0, 1. And then after that, each point is n comma bn, where n is an integer. Actually, n doesn't have to be an integer. It can be any real number, but we just use integers. N can be any real number, but that's how you can find any point on it without a transformation. Those are without transformations. We go with that. Those are the 3 things with exponential. That is if there's no transformation. So this one does have a transformation, but typically they go to that point because if you plug in a 0 for n, what is any base, no matter what the base is, raised to the 0 power? 1. And so you'll end up with that point if there's not transformations. Now this one has one, because you see how we don't go through that. This one, it looks like it's been, the a value would be 3, it's been multiplied by 3. That's why it's not 0, 1, it's 0, 3. But that's where you get that. Okay? Do you have that part's the important part? Oh, it says limits. We'll get there here, and it's at the end of the lesson. Let's go talk about this limit right here. This limit. I'm gonna call this f of x, this equation. What happens as we go left? As we go left, does this exponential fall forever? Does it rise forever, or does it appear to be getting flat and following an asymptote? Flat. What's the y value of that asymptote? 0. That would be that limit. And what about the limit on this end of the graph? What happens as we go to the right forever? Does this graph appear to rise forever? Does it fall forever, or does it get flat following an asymptote? Rises. What you're going to learn is that every exponential function has a domain all reals, meaning x will go from -infinity to +infinity. Not what you're going to learn. Hopefully I remind you what you've seen. Every exponential, the x's go from -infinity to +infinity because the domain's all reals. But the y's will go from a constant to an infinity, whether positive or negative, depends on the problem. But you'll have one that's a constant number, one that's an infinity, positive or negative, for every exponential. One that's a constant, one that's an infinity. Okay? I got 3 more examples of this. So I don't want to spend too much time on this one side. Let's go to the next one. This time, what do you think? Exponential or logarithmic? This one's logarithmic. So this one's technically less than 2.9. So the last one was less than 2.3. This one's less than 2.9. So when we started exponential logarithms, how do we know it's a logarithm? What do we call this? A vertical asymptote. So let's make basically the same statements. The logarithmic function has 3 key features. So this is an inverse. So everything should be kind of like the opposite. Instead of a horizontal asymptote, what does it have instead? Vertical asymptote. That's key feature number 1. On this one, what is the vertical asymptote located at?
2.
That point right there is 2. I know it's tricky here, but it's 1 box over. So we'd actually say it's at
1.
1. Now, what is it 1? Is that the x value of 1 or a y value of 1?
X.
That's an x value of 1. So this is x equals 1, that equation. So this has a vertical asymptote at x equals 1. Typically it's at 0. This has a transformation. Every logarithmic function has a vertical asymptote. Typically, without a transformation, it goes to the point not 0, 1, But what would he go through instead, since it's the inverse?
1, 0.
1, 0. Typically, it goes through 1, 0 without a transformation. This one doesn't go through 1, 0, it goes through 2, 0, because which ways have been shifted? It's been shifted 1 unit to the right. Okay, also, instead of going through the point n comma base raised to the power n, what does it go through instead? There you go, you just do the inverse. Every point can be found doing base to the power of n, comma, n. Again, where n's an all real number, where n is a real number. Typically, we just plug in whole numbers, but. Second to right. Question for you. On the last slide, I said every exponential, on the limits, one will be negative infinity, one will be positive infinity. Will that be true for a logarithm? No. Now that will be the y's. One will be positive infinity, one will be negative infinity. So if I go to these limits, this limit here, what's happening to the graph on this side? I'm going to call this one, well, I'll just call it f of x again. What happens on this limit? Is this rising, falling, or getting flat? I'm sorry, flat meaning horizontal. It's rising. So infinity. Where's the x going? It's actually not going to infinity. X is getting cut off somewhere. Where's it getting cut off? At 1. Now, it's 1 plus, because we don't actually get to 1. Remember, limit doesn't tell you where the graph is. It tells you where it's going. We don't get there, but we're coming from the right side. Okay, and then this limit down here. This time, what's happening to the y values? Rising, falling, getting flat? Falling. So this is a negative infinity. So now the range is all reals. But the x is to go to positive infinity. So the inverse is true here. 1x value on a logarithm and a limit, 1x value will be a constant, the other will be an infinity. Whether positive or negative depends on the transformations. One constant, one infinity, the y's will be from negative to positive, one way or the other. That's always true, always, always, always. Unless you're cutting off the graph and only looking in a certain interval, without a restriction, that would be always true. The y's, yep. It'll rise, it'll be all reals in the range. One end's rising, one end's falling. Whereas exponentials, what's different is it's talking about the domain. One will go left, one will go right on exponentials. Okay, I got 2 more. Let's go a little quicker. What would you say this one is? How'd you say, how'd you find out exponential so quick? What'd you look at? A horizontal asymptote. So this one, we're just going to say exponential. I'm not going to write all the extra stuff. I'm just going to say this is exponential function. I'll just say exponential this time. If you're going to do limits, this limit here, it kind of looks logarithmic, doesn't it? But if you look at your asymptotes, you can tell it's exponential because it's a horizontal asymptote. What's y doing? Is it rising, falling, or getting really flat? It's flat. So this is the constant. What's the constant number it's approaching? 2. You do not have to do a minus or a plus or anything like that on the y's. What about x? Which way is x going? Infinity, going to the right. Okay, and then what about this other limit over here? What's happening to the y's? They are falling. And what's happening to the x's? They're going left. So, like I said, every exponential, the domain is all reals. So your limits will be from negative infinity to positive infinity. But the range is not all real, so it'll always be an uninfinity until and a constant.
So exponentials have horizontal.
Always. Yes.
And for logarithms,
Vertical. Yep.
always.
Always. So horizontal asymptote will be the number on the one limit that's a constant, whatever that is. No matter if you're talking about exponentials or logarithms, whatever your asymptote is, in this case it's y equals 2. That's going to be the constant that fills in the limit.
the x's were the limits, they were going to be.
Yes, for exponentials, because they're all reals. Exponentials are all reals on domain. Logarithms, the range is all reals. So that's why on exponentials, the limits are a negative infinity and a positive infinity, because that's the all real domain. On logarithms, it's the range, the y's, the f of x, that'll be negative infinity to positive infinity, because that's all reals. Okay, I got one more to make sure you got this down. One more. Don't call it out this time. Let everybody look at it for, I'll give you at least 6 seconds. All right, what do you think? Exponential logarithms, 5, 4, 3, 2, 1.
Logarithm.
Why is it a logarithm? You saw vertical asymptote. It's the easiest giveaway. It's the asymptote. This has a vertical asymptote, therefore it is a logarithm. Where is that asymptote located? Because this would be our constant for the limit. It's at -5, and is that a y value or an x value that's cutting through there? X. This is x equals -5. So that will be the one constant value. So your limits, the only limits you should expect to see on a test over exponentials or logarithms, will only have infinities, negative infinities, except for one constant. That one constant is going to be the asymptote -5. Let's plug it in. Tell me about this limit over here. X. Is it rising, falling, or approaching an asymptote, getting flat? It's rising. There's no asymptote. It's got to be rising. It's rising very slow, but it is rising. What about its x direction? It's going to infinity. Okay. Tell me about this other limit down here. Rising, falling, getting really flat.
But.
Flat, that means horizontal when I say that. What's happening this time? It's falling, negative infinity. So far, there's all of our infinities. You're gonna have 3 infinities with exponentials and logarithms. You'll always have 3 infinities. You'll have one constant. It's got to be the x. What's the constant the x is approaching? -5. Now, are we approaching that from the left side or right side?
Left.
Right. On the x values, if you're approaching a constant, we typically will have a plus or minus. Very few situations will you not see that. Questions over that? Good. I'm gonna totally switch gears. So that was lesson 2.3 and 2.9 a whole bunch of times. I think 4 different times I showed you lesson either 2.3 or 2.9. Moving on to the next. Oh, can't move on yet. So let's see what you learned. Almost like a little quiz here. How will the end behavior of an exponential function always be described? I want you to think exponential, what it should look like. How will every limit be described on an exponential? What will be true of the x's? So if it's all reals, that means one's a negative infinity, one's a, what's going to be true of the y's? No, not for exponentials. So if your x's are all reals, so here's what will be true no matter what. You'll have one limit that's going to have a, say, negative infinity, and you'll have another limit that's going to have a positive infinity because it's all reals. What will be true of the y's though? One is going to be a constant. One's going to be infinity. We don't know which one it is. So if the negative infinity has the constant, then the positive infinity would have a positive or negative infinity over there. It could be positive, it could be negative. Depends on the problem. But what if this has the positive or negative infinity? Then in that case, this becomes the constant. So there's 2 situations. It's either constant, positive and negative infinity, or it's positive, negative infinity, constant. But either way, you'll have negative infinity and positive infinity. Either way. Okay, so what's the relationship between an exponential and a logarithm?
We switch.
I hear switch them. Switch what?
Switch limits.
Switch the x's and
The y.
the y. So basically, I'm going to write this all over again. Except this time, we're going to do our slashes on the x values, not on the y. So we'll have a limit f of x equals, no matter what, this will be a negative infinity and your other limit will be a positive infinity. No matter what, that's true. Because now the range is all reals. But what's going to change is your x could be the constant on this side. And if it's a constant on this side, then what's it going to be on over here? Positive or negative infinity, depending on the transformations. But what if it's not a constant? What if this side has the positive or negative infinity? Then what does it mean on this side? Then it's the constant. And again, you'll have a little plus or minus on your constant. Questions over that? Okay, I'm going to skip a lot of what we did on lesson 2.4 and 2.5, and it's equal lessons 2.10. Those had to do with properties. I'm going to save the properties till we come to solving problems. I'm going to put those all together at the end where we just do inverses and solve together, okay? So I'm now going to skip and do the tables. Looking at tables and determining if it's exponential or if it's logarithmic and writing an equation from that. Okay, so if you want to go in order, sorry, I'm going to go out of order. The properties I'm going to put at the end with solving. Let's take a look at tables. The first question I think I put like 6. If y'all get tired of doing them, if you're figuring it out, just tell me, we can move on. I did a bunch just in case you struggled on the tables. The first thing I want to determine is, one, is it exponential or logarithm? Because you can probably eliminate 2 answer choices and make the problem become 50-50. 50% of getting it right on a pure guess is better than 25%. So first we're going to determine that. Just, is it logarithmic? Is it exponential? And then we're going to do the harder part, which is let's write an equation without it. Okay? So first, what type of data is this as you look at this table? Exponential or logarithmic? How did you know? This is logarithmic because the x's are multiplying and the y's are adding. Here's what we're going to do. On the adding side, we're going to write that down first just because it's the easiest. How much are we adding by each time here? 6. Great news for you. If you're adding on the y side, that is always your a when it comes to writing the equation. I'm going to go ahead and just put that there. That is your a. If, hear me, if it's on the y's. It's not true if it's on the x's. If it's on the y's, that's a true statement. That is your y's. Your a's, I'm sorry. Excuse me. Your a's. X column. What are we multiplying by every time? 3. Now, if it was hard to tell, I would do a change of x to figure out exactly what we're multiplying. But there's no transformations. What are we multiplying by each time? 3. The value you're multiplying is what we call the base. And so here I'm going to write base once, but the variable we say is 3. I already wrote this once today, but I put this here just to help you in a second for solving these. So now let's do the harder part. Question 2. What equation would fit the data? Now you told me it's a logarithmic function, correct? For a logarithmic function, they use the letter f of x. F of x is going to follow this model. It'll be a log base parentheses x minus h plus k. That's as complex as we're going to get right there. That's your general form. As complex as we'll get, or as you want to get, will be right there. Now, what values from this equation have we already solved for?
A and B.
A and B. So I wish I had a little bit more space, but I'll fit it in. Here's what we already know is true. We know A is 6. Our B is 3. That's what we know. And I'm going to stop there. That's what we know so far. So how can you get the rest? Well, we start plugging in numbers and seeing if it follows this, because if it excuse me, I'm circling the wrong one. We're going to see if it follows this pattern, because if it does, we don't have any transformations. Remember, this is the pattern if there's no transformations. So let's plug in the first value. I'm going to plug in a 0. I think it's the easiest. If I plug in a 0 here, what's my base on our actual problem? So let's try plugging in, it's 3. If I plug in the value 0, 1, what I'm saying is, in this case, x becomes the n. Let's say n equals 0. I'm sorry, y. The y is the n. So I'm plugging in 0 here. Am I doing this right? For this point here, if I plug in a 0, yeah, that goes to 0 there. Okay, we're going to check to see if it matches up this point. So I plug in n of 0. What do you get if you plug in a 0 there? What's 3 to the 0?
3.
Now 3 to 0 is not 3, it's 1. Now, does that match up with our table? This is a good thing. That means there's no other transformations. Let's check it again. What if I did it one more time? Let's say now n is 1. I'm just picking a number. It doesn't have to be the number on the table. I'm looking, 1 might not. Yeah, 1 will work. Let's say we plug in a 1. So now my base is 3, and we're going to plug in a 1. So plugging in a 1, that means 3 to the first. I'm plugging in n of 1. 1 there. Okay, what's 3 to the first? 3, and well, 1's just 1. Does that match up? Do I have a 0.31? No, because why not? It comes down to this a right here. You see how that doesn't match up perfectly? Because there is one transformation. What are we supposed to be doing with a? Multiplying by 6. And so this actually does work perfect. If you took your 6 and multiplied these, if you're like, oh, okay, now that I'm getting this, what this means is I have an a that's multiplying the y values. What happens is this needs to be multiplied by a, which is 6, and this needs to be multiplied by a. If you came back, you'd realize, what's 6 times 0? 0, so it'll still work. What's 6 times 1? 6, and so it would work. This is right. Another way you could do this is just by plugging in a number over here and checking. Okay, so for example, I'm going to put a minus h plus k here, minus h plus k. You could plug in numbers and start seeing if it works. If I plug in a 1, basically you're saying 3, I'm getting ahead. How am I? Okay, it doesn't have any transformations. Let me go to one that does have transformations and you'll see how it works, okay? I'm getting lost on how to explain this. This doesn't have any transformations other than that 6 right there. We'll see it in a moment where they do, though. Getting lost in my head how to explain that this doesn't have transformations. Let me show you one that does have transformations. It'll make more sense. Okay, let's go to the next problem. I told you got like 6, so I got plenty here to look at. Don't quit if you get confused on number 1. This time, what function are we looking at here? Exponential. This is exponential. That's the first part. If you can get that, your problem's 50-50. How did we know it was exponential? X's are adding. How much are they adding by? Now, that is not necessarily going to be equal to a. Our a might be 1, but it does not have to be 1. Because a is a vertical translation, a vertical dilation, I should say, vertical dilation. This right now is telling me about my horizontal dilation.
The x's are the. Oh, yeah.
Now, a is always from the y values. Always, always, always. Y goes, yep, because a is on the outside. Okay, so when we rewrite the equation, here's what the equation should look like. So they call this one g of x. Here's the standard form for an exponential. It's going to be a times b. You don't have to put the parentheses there, sorry. A times b, and let's do the parentheses here. X minus h plus k. Okay, let's start solving. Let's get our base first. We don't know what our base is yet. Can you tell readily, like, is this one, is it easy to tell what we're multiplying by? No. I can tell it's changing crazy, so it must be multiplying. What I'm going to do is create a new table, and I'm just going to call it change of y. I'm gonna call it A rock, even though this one would be A rock. I'm just gonna call it change of Y, so that when I do the X, it'll look the same on each problem. Okay, what are we changing going from 4 to 5? 1. How much do we change from 5 to 7? 2. How much from 7 to 11? And then how much from 11 to 19? Okay, the change in Y column, you can also get your base from there. It'll still be the same base, even though we've changed our numbers. If you do the change of column, this will always give you a perfect multiplication if it's exponential or logarithm. It doesn't change the values, but it will show you what's happening. What is our base this time? Now it's easier to tell. What are we actually multiplying by?
2.
We're multiplying by 2. Did I do it as an x times? Yes, I did. Okay, x times 2, x times 2, x times 2. That is my, what letter would that be? Nope, not A.
3.
That's our base. The one that's multiplying is your base. Our base equals 2. Now, from the change of column, you can tell if there's been any vertical translations. Now, how can I tell this? If you have a vertical translation and your A is 1, let me say this. You can tell if A is 1 or not 1 by if these are all off by the same amount of numbers. You see, what's the difference between 4 and 1? 3. What about here? 3. What about here? What about here? So these values are not getting multiplied by anything, but they are getting added by 3. You have to add them. You have to add 3. And I'm going to check real quick to make sure I'm not telling you that that's not going to become a -3. Let me check real quick. Where's my table here? 0, 4. Yeah, we have to add 3 over here to get this column. So I'm going to do like a +3. What does that mean? When I write my equation, what I just determined is because I have to add 3 to this column to make it be this column here, this is a +3. So here's what we now have. We have g of x equals a, and we know our a is actually 1 since there's no multiplier, since these are say the same amount off. Let me say here, I'll put the note, a is 1. A equals 1 since g of x equals change of y plus 3 without a multiplier. And that's why a equals 1. So my a is 1, so I don't even have to include in the equation. What's our base? 2 power x minus h plus, which is 3. Okay, last thing. Let's plug in a point to see what h is. If you start plugging in points, you know what? I wanted to show you. This is a way with property. There's a property. I hate it when I do this, but I'm going to change in the middle. An easier way of even solving this is your h. Do you remember your exponential properties? I'm going out of order. I told you I was going to do this at the end. That we have what's called the quotient property, which said if you're subtracting here, do you remember that a horizontal translation can become a vertical dilation? Do y'all remember that lesson? We talked about that. I'm going out of order here. You can actually solve this for a without even using an h, which is probably the easier way of doing this. I'm going to scratch because all of a sudden I'm thinking about this. This will be the easier. I should have taught it this way from the start of class. Here's the way we're going to solve this is I'm going to ignore the h on exponentials and do it this way. I'm going to do b to the power of x plus k. Now, why do I say that? Because this will be much easier for you to solve. What I can do is I've already solved for the base, and I'm just going to stop and act like I've only solved for the base. Okay, we're going to plug in 2 values, and I'll show you how this will work. I want to plug in 0 and 4. 0 is my x, 4 is my g of x. So just start this problem fresh right here. What I'm going to do is g of x is 4. You see how g of x is 4? Make sure everybody's tracking. And I want to pretend like I don't know a. I'm going to pretend like I haven't found that. Let's say a, we do know our base. What's our base? Just put a 2 there. We do know base outright, so I'll put a 2 there. So it'll be a times 2 to the, okay, in this problem, what's our x value? If g of x is 4, what's our x? 0 plus k. And now I will simplify this. What is 2 to the 0 power? 1. So I have 1a plus k. And I'm going to stop for a second. And now I'm going to do this again. I'm going to plug in a different point. Let's now plug in 1, 5. 5 goes into g of x. So I'm going to say 5 equals a times 2 to the, now what's my x this time? 1 plus k. And we'll simplify that. I have 5 equals, what's a times 2? 2a plus k. I could use these two equations together to solve my problem. I'm just going to subtract these two equations. I'm going to take this one because it's a bigger number. I like dealing with positives. And I'm going to say 5 equals 2a plus k. And what I'm going to do is subtract the other equation. 4 equals a plus k. Now, before I tell you why, I want you, don't say it out loud, give everybody a chance to think. I want you to think, why did I decide to subtract these two equations? Look over here and hopefully you'll figure out, why am I subtracting the two equations? Give you a second to think. Yeah. Okay, what do y'all think? Why did I choose to subtract them? Because the variable k will disappear. And so what's left over? What's 5 minus 4? 1. What's 2a minus a? A is 1. And so now we have that variable. And now that I have that variable, I can just plug that into either equation. Since I have this one right here, we'll plug that in. And so now we'll say, instead of 5 equals 2a plus k, I'm just going to say 5 equals 2 times 1 plus k. What's 5 times 2 plus k? 5 equals 2 plus k. I said that wrong. 5 equals 2 plus k. What is k going to be? That's correct. We subtract 2, we find out k is 3. Now that is probably that's the better way of teaching you, so you're not guessing from all this table stuff I was starting to do there. So I'm going to take this away so you're not confused by it if you look at this later on. I'm just going to leave it like that. There's your algebra. I'm going to take that away, change this equation. So that's how you can solve that. You don't have to do the minus h because a horizontal translation is the same thing as a vertical dilation. That was a property we learned on the exponential function manipulation. I think that was lesson 2.6. All right, I'm going to do another one. I told you I got a bunch. I don't want to confuse you, so I'd rather you see it a bunch of times rather than be confused one time. This time, first off, let's make it where you're 50-50. Where worst case scenario, you're making a 50 on the test rather than a 25 on the test, going off pure statistics. What type of function would you say this is?
Exponential.
I hear exponential. Why exponential?
Because the x's are adding.
X's are adding, and what's happening with y's? Is it a consistent change? No, it looks weird. So put a b to the power of x plus k. That's going to be our formula right there. All right, let's start filling in. This is changing my ones. Will that be my A? I'm going to say this a bunch of times. Is that necessarily my A? No, because it's the X column. A doesn't deal with the X column. What what column does A deal with? The Y's. So that's not A. Can we tell right away what this is being multiplied by? Is it easy to tell or not so easy to tell? Not so easy. Let's add a column. What should we call this column? Let's do change of Y's. Let's do a change of Y column. Okay, how much do I change going from negative 0.5 to 0.5? We increase by 1. What about from 0.5 to 3.5? We increase by 3. What about from 3.5 to 12.5? Increase by 9. What about 12.5 to 39.5? 27. Okay, this cleans up our data. Now we can see what is it that we're actually multiplying by. We're multiplying by 3. So what does that tell us? The base, not the A. That tells us our base. So our B value equals 3. Now what I'm going to do is just plug these in and we're going to solve our equation. So now we know g of x equals, do we know A? Do we know B?
Yep.
B is 3 to the power of x plus k. So how can I solve from here? We can plug in some points. Which point do y'all want to plug in first? Do you want to do this one or ignore that, the negative, and go to the next one? What do you want to do? Start with 3? Deal with positives? Okay, the 0.5, what is that value? The y. So 0.5 equals a times 3 to the third power plus k. So let's simplify. What's 3 to the third? That's 3 times 3 times 3. 27. That will be 0.5 equals 27a plus k. Okay, now what did we do last problem after we did that? We did a second point. Which point do y'all want to use this time? Do you want to use 4? That's going to be getting us a pretty big number there because 3 to the 4th. We want to use squared. Let's say we're not scared of the negative. Let's go with that. We're not scared of the negative. Let's do the negative. If we did plug in negative 0.5 equals a times, I put a 2 there, sorry. Base is 3 squared plus k. I plugged in a 2 for x and a negative 0.5 for g of x. Let's simplify that. What is 3 squared? So we have negative 0.5x, negative 0.5 plus 9a plus k. Okay, do you remember what we did from here? Let's subtract the 2 equations. I'll just list this one first because I see the a's are bigger. I think it'll be better to do it that way. So I'll take the 0.5 equals 27a plus k. And we are going to subtract negative 0.5, no, not close parentheses, sorry, equals 9a plus k. Now, before you call it out again, I'm gonna let you take a second to look at it. Why is it that I'm subtracting the equation? What does that benefit us, subtracting that equation? It eliminates the k. I didn't mean to do that. This is a negative of a negative. So what do I do with that 0.5? Add it. What's 0.5 plus another 0.5? 27 minus 9. 27a minus 9a's. 18a. And so what does a actually equal here? One over 18. I agree with you. A is A is 1 over 18. And so now I can choose any equation. Let's just use this one. Negative 0.5 would equal 9 times 1 over 18 plus k. What is 9 times 1 over 18? Or what is 9/18? 1/2. So negative 0.5 equals 0.5. I'm changing to a decimal. Plus k. How would I solve that? Subtract 0.5. It'd be subtraction since they're adding together. And we now will get our k value. What's negative half minus another negative half? Negative 1 equals k. And so we have all of our answers. Let's go ahead and write our final equation. G of x would equal 1 over 18 times 3 to the power of x minus 1. There's your equation. Now, I said it earlier, I have a whole bunch. Just tell me if you're like, hey, I got it down. Just tell me if you come to that point. Hopefully you're seeing the strategy here. I'll tell you this, you don't have to write that many equations. Don't just be thinking, oh my goodness, how many times am I gonna have to do this in the test? You don't have to do this that many times. I'm just getting the skill. If you got the skill down, you're great. Again, I told you it's 50-50 if you can just look at it and tell me. And again, this is not all your problems. We had 15 lessons. It's 50-50 if you can just look at this and say, hey, it's exponential, it's logarithmic. What do you think this time?
Logarithmic.
This is logarithmic. Why is it logarithmic?
Adding by 3 and x.
Now, close. You said it's adding by 3. It's not actually adding by 3, it's adding by 2. Okay, what is that adding by 2 if it's in the y column? Do you remember? That is, whoops, I wrote A. That is your A. That's the nice thing about the logarithm is we now know if it follows this log base, because of properties, I cannot change this x minus h. You have to have that x minus h in there. What I can state right away though, is we now know our A is 2. A is 2. Let me write the word log. Okay, come over here. Is this just a straight up multiplication like our first logarithm where it went 1, 3, 9, 27? Is this a pretty little multiplication? No. So what should we do if it's not? Add a column, and what do we call this column that we're adding? The change of x. All right. How much does it change going from 3 to 5? And how much from 5 to 9? Or how much from 9 to 17? 8. How much from 17 to 33? 16. What's happening on all of those? So that means what does that tell us? Our base is 2. We now know this is a 2. Okay, so what I do on logarithms, I think this is the easiest way to do it, is because x's come before all transformations. Remember, when you look in, you start from inside out. The x values themselves come before any other transformation. What's easiest to do is to make sure that this is the initial point of if you're doing a logarithm. I'm talking about a logarithm now. If it's exponential, I would do it the way I showed you. If it's a logarithm, to make sure this is your initial value, meaning like your asymptote. I think the easiest way is to find the asymptote here. Now, you might be going, Well, how do I know it's the asymptote? Here's how you know. What's happening every time on the change of x? It's multiplying by 2. Now, is that the first power of 2? Meaning, is it the point? Remember how it goes b to the n, comma n? Is that this value right here, b to the 0, 2 to the 0? Is that equal 2 to the 0? No, that's 2 to the first. What I mean by that is there's another point in here we could add to our table. I'm going to add a point. Now, I know I can add a point because this is changing by 2. I should have a point where I have 2 to the 0, comma 0. Now, what is 2 to the 0? I need to have one that says change of 1. So what number plus 1 equals 3? 2 goes there. And these are always adding 2. So what number plus 2 would equal 5? 3. That's your initial value that we're going off of here. This is actually the initial value. All that to say, our transformations we could figure out from this one here. You could do it that way. Or if that confuses you, here's one more way. Again, x's are before the transformations. This takes away the transformation right here. What's the difference between these values? These are always 1 greater. So if you took 1 away from the x's, you'd have your change of x column. That's another way of doing it. It's just saying these are 1. You see how it's 1 greater? If I took away 1, I get the change of x that I need for my logarithm. So that value right there is what goes in for h. So what I want to do here is I'm going to put x minus 1. Now, how do I know that? Is because these are always 1 off. So you don't even have to find that point. I gave it to you, but if it's confusing, then don't worry about that. Just look at it and say, okay, I see what's going on here. This value, because I'm dealing with x's on logarithms, this is before the transformations, they were 1 off every single time. So I need to subtract 1 from this column to make it right. If I take away 1, I can find the logarithms. So we have all that. The only thing we're missing is our k. So how can you find the k? Well, let's just plug in, and we only have to plug in 1 point. I'll show you. 3, 5. Let's plug that in. 5 is our f of x. We know a is 2, so it's log 2. What's our x on this first problem? First point we're plugging in? 3 minus 1 plus k. Right now I'm solving this for k. I'm going to erase this. That's just going to be extra and confusing later on. So we don't need that. Okay, and we'll solve here. What is 3 minus 1? 2. So this is saying log 2 of 2. What is log of 2 of 2? 1. That value is 1. So this is 5 equals 2 times 1 plus k. What is 2 times 1? 2. So 5 equals 2 plus k. You probably know what k is. How do we get our k there? Subtract 2. What are y'all getting? Are you getting 3? That's going to be our solution here. Our value is going to end up being a 3. So now come back up here, erase that k, and I'll put it as a 3. That is our equation. Whoops, I covered up the base. Try that again. So a logarithm, you don't have to use 2 equations if you can get the data from over here, but you have to mess around with it a little bit. What's nice about a logarithm is you can discover a from the change of y's. You can discover your horizontal translation looking at these values as well. Okay, how are we doing? You want to do more? Or you want to switch to something different? How many say switch? Got quite a few. Let's do a switch and then I'll come back at the end if you want to see more. How about that? Okay, yep. Go ahead. Without solving them, let's just write on the side. Let's just make it 50-50. What would this one be? Exponential, logarithmic? This would be exponential. How'd you know exponential? X's are adding, Y's certainly are not adding or subtracting. That's exponential. Okay, what about this one?
Logarithmic.
Logarithmic. Okay, new problem. If, does that say IN? Like I'm inside of a building? No, what does that mean right there? Natural log. A log with a base of E. If it said log without a base, that's base 10. Ln means base of E. If natural log A equals 2, natural log B equals 3. Oh, I meant to change this. If you're writing this down, don't write the 5 there. Put the 5 here. Evaluate log B A of 5. Okay, this is lesson 2-13, but it also includes the properties from chapter 2. Chapter 2, lesson oh, I forget. Is it 2.5 and then 2.10? So this is lesson 2.5, 2.10, and 2.13 that I'm going to do all in one. All right, how can I evaluate this? Well, I would need to use some properties. Here they gave me log base B of A to the 5th. I'm dropping the parentheses. I don't need them. What could we do here to try to solve this problem, do you think? What properties could we do? We could do power property. What can you do with a logarithm when you have a power? It multiplies. And it doesn't have to move to the front. That's how I've said it. But it could, appear at the back. You could make it, put a parenthesis around the A and put it after. As we did see that one, what's it called? AP classroom problem that I showed you a few lessons back where they are making it multiply at the end. Okay, so we now have that. That's based off the power property. Okay, now what could we do to try to solve this problem? Guadalupe's got it. He says change a base. Right now, do I have the same base with these 3 logarithms? What's the base here and here? E. What's my base right here? It's just a B. Is that the same base? No. So you can change a base. Remember how that works? Instead of saying 5 times log base B of A, you can change whatever base you want. What base should we pick? Can't say E. What base should we pick? E. We want a base of E to get them like these. And so I'm going to do this as the natural log of A divided by the natural log of B. This is the change of base property. Change of base property. Now, notice I did not cancel the A. I did not cancel the B. But it becomes a different log of A divided by whatever that log was of B. You could pick any base you wanted to. I could have done base of log 7 of A divided by log 7 of B. I could have done log 3 of A divided by log 3 of B. You can pick whatever base you want. But you just have to make it the log of the original value divided by the log of the base. That's change of base. How can I solve from there? I just substitute. What do we know about natural log of A? What do we know about that? It's 2. What do we know about the natural log of B? It's 3. Now that I just did substitution. And now we'll simplify for our solution. 5 times 2 is 10. You only multiply with the numerator. It's 10 divided by 3. Can I simplify that? There's our answer. Okay, let's try this problem. If log base 3 of A is 2 and log base 9 of B is 3, evaluate log base 27 of A times B to the power of -2. Oh, man. Where do we start? Do I start with log 3a equals 2, log 9b equals 3, or do I start with log 27, all that? Let's start there. Log 27 a times b to the power of -2. I wrote it like that to give you a hint. How do you think we go from here? I hear power property. I also heard product property. I'll give you a hint. It is one of those two. Which one will we have to do first? Can I move the -2 to the front? I mean, why not? It's only on B. It's not on the A. So I need to first separate these two. What can you do with two logs that are multiplying? They become two different logs that are now adding. Now, for those, some of you are thinking, doesn't this mean it's truly dividing by b squared? Yes. And it would be quotient property? Yes. We'll get there anyways. But I'm going to act like we don't know that. So log 27 of A, one log multiplying becomes two logs, two or more logs adding. Log base 27 b to the power of -2. What property was that? Product property. Okay, what do you think now? Power property, very good. What can I do with this power here? I can multiply with it. You can do it in the front or the back. I'm going to do it in the front. You make. So this will be log 27a. I'm not going to do a plus a -2. I'm just going to change it to a -2 log 27 of b. That was the not quotient property. I'm sorry. That was the power property. Now what? When I look at this, do I have that right there? What's the problem? We need a different base, don't we? Do we have a way of changing the base? Change a base property. So I'm going to write log of, and for this first log, this one right here, what would I choose for A, the base to be? And I'm going to point this out because B is going to have a different base. What do I want the base to be? 3. So it's log base 3 of A divided by log base 3 of 27. Good. That's ugly. Let's try it again. 27 minus. Now let's talk about this one. We're going to do a different change of base. On the B, what do I want the base to be? 9. So log base 9 of B divided by log base 9 of 27. That is change of base. Now I'm just going to copy and paste this so I can begin again down below. Okay, so for beginning right here, now we can start simplifying. All right, what do we know about log 9 of A? Can we say it's true about log 9 of A? Oops. Log 9 of, not log 9 of A, I'm sorry, log 3 of A. Log 3 of A is 2. So we just evaluated this. We're gonna substitute and say that's 2. And what about log 3 of 27? 3 to what power is 27? Very good. So we are evaluating and substituting here. Substituting and evaluating. Minus 2 times. What about log 9 of B? What was that? That's 3. And log 9/27. This one's a little bit harder because if you think about it, 9 to what power is 27? Doesn't go in evenly. 9 can go in, I'm doing upside down division 3 times, but that's not the same number. So really how you break this down is what number can go into 9?
3, and 3 goes in twice to 9. So since 3 squared is 9, but as far as 27 is concerned, it takes 3 3s. 3 cubed is 27. What does that mean here? Log 9 of 27. Since 3 goes into this twice and 3 goes into this 3 times, if you did another change of base, which I'm not going to write out, it'd be log 3 of 27 over log 3 9. You would have 3 divided by 2. This is going to 3 divided by 2. That's what that is. 3 divided by 2. It's because 3 goes into 9 twice, 3 goes into 27 3 times by power. Now, all that was substitution, and evaluating logs. That's all that was right there in red. Now let's just simplify to get our answer. All right, I have 2/3. I don't know if you remember what you do when you have a fraction divided by another fraction, but what it becomes is you take the numerator and then you multiply it by the reciprocal. So instead of it being -2 times 3 divided by 3/2, it becomes -2 times 3 times 2/3. I just took the reciprocal there.
So what is the towards?
Say it again.
What does it say towards?
Shouldn't. Sorry, losing my mind. 2/3. 2/3 minus 2 times 3 times 3. Okay, I'm good now. This, instead of dividing by 3/2, we're going to multiplying by 2/3. Once we simplify this, we'll have our answer. It all has a denominator of 3, so it becomes 2 minus, what's 2 times 3? 6 times 2? 12. And that equals, doing all that work, we're finally at our answer. -10 divided by 3. Purely a coincidence that the last problem was 10/3 and this is -10/3, but that's how you do those problems. All right, switching gears. If you see a graph like this, there's a name for whenever you have weird graphs like this. It was semi-log plot. The important thing you need to know, if you're working with a semi-log plot, the important thing you need to know is the transformation that occurs that makes it happen. Now, just look at the values you should be able to find out. Looking at the x's, do the x's look like they've been changed? If you look at the y's, do they look like they've been changed? Yeah, they're counting weird. How did we get these weird values? What we did is we took a log. I'm answering this question. What transformations occur? We take the log of the y values. So you take a log of the y values, a common log. So what does it mean to be a common log? Log base 10 of the y values, which means a lot of times you might see it written this way. You might see it log of f of x, because what does f of x represent? Y. Now, I want to make sure it's clear. Do we change our data? Do not change your data. Do not change your data. What do you change? Just the y-axis. Now, I want to point out, why is it 1, 10, 100, 1,000? Because the count by powers. 1 is the same thing as 10 to the power of 0. 10 is the same thing as 10 to the first. 100 is the same thing as 10 squared. You see how these lines, this bold line, this bold line, this bold line, they're counting by powers. Does that make sense? That's how it works. Now, does that mean I took 10? I took the y's to the power of 10? No, I did the opposite. I took the log of the y's, and it makes it look like that. Okay, so let's look at an example. What if we had to plot these points? So if I give you this, let me just create a table. How about that? And it's y equals 2 times 4 to the power of x. We'll plot maybe 4 points or so. 0, 1, 2, 3, and 4. So what corresponding y values will we get when we plug this in? What is 4 to the power of 0? What's anything to the power of 0? 1. 2 times 1 is 2, okay? I plug in a 1. What's 4 to the power of 1? 4 times 2? Okay, we plug in a 2. What's 4 squared? 16 times 2? You can see the pattern now. What's happening each time? It's multiplying by 4. So 4 to the third power, that's 64 times 2. 128. And now if you plug in a 4, oh my goodness, it's gonna be a big number. That's 64, 256, very good. Times 2. 512. There's the data we'll plot. So let's go as best as possible. Now, is that 0, 0? Is the origin 0, 0? It's weird. It's 0, 1. So I need to plot 0, 2. I go up just one line. That's 0, 2. And then we plot 1, 8. 1. This is 8 right there. Because that's 1, 2, 3, 4, 5, 6, 7, 8. That's 1, 8. Then I would plot 2, 32. 10, 20, 30. 2, that's 2, comma 32. 3, 128. There's 100. How much is this right here? 200. So 128 is somewhere in there. 3, 128. And then finally, 4, 512. That's 100, 200, 300, 400, 500. It's going to be barely bigger than 500. 4, comma 512. Now, how does the data look when you look at that? Linear. It's very important you know that. Why does it appear to be linear? Because it's a log of the exponential data. Remember how I just said we take a log of the exponential data? That's why it looks linear. This is linear. I want to make sure you understand how the equation now is formed. This equation right here. Now, truthfully, what is the equation for this line? 2 times 4 to the power of x. If you're going off of slope and intercept, this does not have, this would act like your intercept, you know, it doesn't have anything. You wouldn't think it's just one mark up. How you would find it here is you would do this. How it works, I want to make sure you know that. I'm going to call this y hat. Y hat. What I mean by y hat is the equation of this line right there. How the equation's built is this. The slope is the log of the base. That's the slope. That's your m. So I'm doing the equation of a line as far as mx plus b. That's what I'm doing here. It's the slope is the log of the base. Your y-intercept is the log of the a. I don't need a parenthesis around that 2. Sorry, it's just a 2. I'll do it like that. That would be that. So what do I mean by this? Let me just show you quickly on my tape calculator. If I go to calculator, now calculator, and I type this value in, this is telling my slope. If you're like, what's the slope of this line? Well, it's whatever log 4 is. Log, I'm going to skip the base. What's it mean the base is if I skip it? Okay, my slope is 0.6. That means it has a rise of 0.6 for every unit you go to the right. Say it again. My slope is 0.6. Now remember, over here, it counts by powers. That means from this point, if I go 1 to the right, I go up 0.6. So if this is 1, this is 2, this is 3. Do you see how this goes up a little bit more than halfway between what looks like the x-intercept and this line here? Do you realize how I go up just over halfway? That's because it's the log of my base of 4, which was 0.6. Follow? So I'm going to write this down as approximately 0.6x. And then let's take log of 2 to find the y-intercept. Log 2. Now remember, this is 0, this is 1 on a normal graph. 0, 1. So this linear equation is given it to me in terms of normal, how you would think of it. It's 0.3. Means you're just 3/10 of the way up. Close that off. And so back over here. Plus 0.3. That would be the equation that right here. That represents how the data looks. Just to be quick, how would I get this equation I just wrote down back into this form? What's the opposite of a log? Exponential. So if I did 10 to the power of 0.6, 10 to the power of 0.6, what would that give me? I did 10 to the power of the slope. Would that give me the A or the B? B. That would give you the B. If you did 10 to the power of 0.3, what does that give us? A, 2. That's how you go backwards. Questions over semi-log? That was lesson 214. Go ahead. All right, let's start solving. All those other lessons that I've skipped over so far. Let's start solving here. It says if g of x equals log 9 f of x and g of x equals 0.5x plus 2, what is f of x? So when I gave you all that practice AP classroom exam last class, you had a few of them in this form. What did you do to solve problems like these? Guess? That's funny. That's funny. Well, if you don't want to guess, what if they give us two values that are the same? What do they share? G of x. Let's do a substitution. Instead of saying g of x, I'm going to take what g of x is equal to here and set it equal to this one. Make sense? I'm going to say log base 9 of f of x equals 0.5x plus 2. Now, if y'all can get that far, I bet a lot of you are better equipped for this test than you think you are. If you can just realize, oh, I just do a simple substitution. That's all I did there, is I just did a substitution for g of x. That's all I did so far, is I substituted out g of x. I bet you could solve that. What do you think you need to do from here to get to solve this? The inverse. I have a log that's isolated. What's the opposite of a log that's isolated? Exponential. Yep, it's base, and instead of this, these two switch. I was talking to Dr. Milano this morning. He says, anytime you're solving a log, just do around the world, meaning instead of 9 raised to the power of f of x, he goes 9 to this equals that. He says do around the world. I liked how he said that. So what do we end up having? It's basically how Delta Math teaches you. Raise both to the power of 9. That's what you're doing. These two cancel each other out. And so what you're left with is f of x equals 9 raised to the power of 0.5x plus 2. And I really don't need a parentheses there. I'm going to take away the parentheses. 0.5x plus 2. Now that's mathematically accurate. That is the answer, but that's not the form they wanted. So let's do our properties to get it in the form that we're going to need it in the test. What can I do when I have a power that's adding together? Remember your properties? We called that a product property. If you have a base with adding powers, what you can do is multiple bases, but those bases now multiply. So it's 9, 0.5, 9 to the power of 0.5x times 9 to the power of 2. That right there is called the product property. Product property. That was for exponentials properties. Now 9 squared is going to become my a. So this time I want to put this in the front. That's a constant. What is 9 squared? 81. That's my a. Now I can do a little bit more work on my base here. Now I'm going to do the 0.5 here and the x out here. Now that is a property. When you have a base that a power that's multiplying, so over here it was a power that was adding. Now I have a power that's multiplying. I can change it and break apart the powers like this. What do we call that? Power property. Power property. Power raised to a power is equal to the powers multiplying. So now I can simplify to get my final answer. Do y'all know what 9 to the 0.5 power is?
No.
That's a square root. Yeah, it's like 1/2. Which is 3. That's right. I'll go ahead and write one step in between. So if you want to write that way, that's the same thing. Whoops, I already wrote the answer. Sorry. That's 9 to the power of 1/2, which means it's a square root. And so our final answer, the way they want it, is we could say f of x equals 81 times 3 to the power of x. There's your equation right there. Off to the side, I'll put 9 to the 0.5 is equal to 9 to the 1/2, which is equal to the square root of 9. Maybe that's how I should do it for the notes right here. I'll put square root 9. All right. I got a few more of these. You want to snap a picture real quick? Got it? Okay. How do you find inverse? Okay, I think there's something more important to hit than this one. I'll come back to this in a second if we have time. What if it asks about domain? How do you find domain? Do you remember? Look over here. Cheat. Look on the board. What's domain rule number 3? Logs must be positive. So if you're doing domain, the only thing that matters is the values that affect the x's. That's inside the logarithm. Those affect the y's. Y's are going to be all reals. Every logarithm is all reals. We talked about this at the start of the lesson. That's not true of the domain. 3x plus 1 has to be greater than 0. That's what you're solving to find domain. So we could do this in 2 algebra 1 steps. What goes first? Rule 3. Let's do it in terms of a positive. All logs must be positive. That's what I'm doing here. So 3x plus 1 has got to be greater than 0. That's how you say positive. So we subtract 1 from both sides. And so 3x is greater than -1, which means x has to be greater than -1/3. There's your domain. Notice I did not say all x values must be positive. That's not what it is. It's all logarithms. This logarithm must be positive. Let's increase difficulty and try this one more time. Increase the logarithm. I'm doing domain. Do I need to pay attention to the -12 or the +4? No. All I need to pay attention to, according to rule 3, is this portion. What's got to be true of 3x squared plus 2x minus 5? This has to be greater than 0. How would you solve that? Very good. I hear factor. What type of factoring do we have if it's a trinomial like this? X method. Very good. What's 3 times -5? -15. B is 2. Okay. Okay, factors of -15 that add up to 2. It is 5 times 3. The only factors of 15 are 1 and 15 and 5 and 3. It's got to be 5 and 3 to have a difference of 2. Which one goes negative? 3. Now, because that a is not 1, at some point in time, we're going to simplify by a factor of 3. It's going to be this one. So if we want to do it right away, we can. Goodness, keep doing purple. Sorry. That's the one that's going to get divided by 3. So here's how it'll look. It'll have 3x plus 5. And it's the second parenthesis that instead of saying 3x minus 3, it simplifies to become x minus 1. It would have been 3x minus 3, and then we would have simplified. Here we go. I'll finish this real fast. Hang on 1 second, and I'll cut it. That's going to have a 0 where? +1. At +1, we have a 0. This is at -5. 1, 2, 3, 4, 5 divided by 3. -5 divided by 3 is about right there. That's -5/3. This is +1. This would be a upward facing parabola that goes like this. We want to know where it's greater than 0. This is greater than 0 to the right of 1. It's greater than 0 when you're on the left of -5/3. So your domain would be x is less than -5/3 or x is greater than 1. Pardon me? Because of the square. If you plug in a really big negative number, the square, it would cancel out.